So hello again. I hope everybody has joined. I can see that there are still some people coming in. So I will start with the introduction, and I hope everybody will be there. So my name is Yves. I am in charge of the JMAG technical support, and today I will introduce this session dealing about the new feature of the v20 of JMAG. So this version has been released at the end of last year, December 2020. My colleague Ahmed will be the presenter and will also make some demos of those features. At the end, maybe I will show you that you can find also some tutorials to do this demo and to practice this new feature on your own if needed. So I would like also to inform you that usually there are two main new versions per year, and since v20 JSON has decided to release 3 main versions, so one more each year. This is for be more reactive for fitting the needs of the user more quickly. And still, they are the minor release. So those minor release, this is for bug correction. I think they are released each month, something like that. So the main information is that three major new version. So now you will have v20, v20.1, and v20.2. The first one maybe in April, something like that, and the v20.2 maybe in September, and etc. So yeah, let's start the presentation. So Ahmed will go with some topic dealing about solver, mesh, graphical user interface with the APV and the templates, efficiency map, coil modeling, material, and optimization. So thank you for the introduction. So Ahmed, you can start.
Okay, thank you, Yves. So thank you everybody for joining this session and welcome. I think we can just directly go into it. So for the first topic, we're going to be talking about the solver. So first of all, we have improved the GPU support. Here I'm naming two GPU models that have been tested. And with this improved GPU support, what we offer is the ability to calculate also circuits. So before we had the limitation that you could not run circuits, you had to apply current density condition. Now you can implement the JMAG circuit within the GPU solver as well. This can also be linked with a SMP solver. So both a GPU solver and an SMP solver, giving up a speed up ratio of up to 12 times. This is perfect for middle-sized models. So within the 1 million to 8 million element range. Also 8 million is a bit, on the edge, let's say. We also, I've named two models in this presentation, but also we have another third model and a few extra models that are named on the JMAG website. For the second option, we have an improved workflow for the calculation of electromagnetic forces. And this offers the capability of calculating electromagnetic forces using post-processing. So by means of a batch file, you can calculate the electromagnetic forces on the teeth or in the rotor, or just calculate the torque if you, for some reason, have forgotten to implement the torque condition. What this offers also at the same time is a very high speed up capability. Since you're not calculating the forces transiently and you're doing it in a post-processing method, you're saving a lot of time. And here in the graph shown, there was a test run on a model of 6 million elements for 33 steps on 64 cores. The left one shows the calculation being done on version 19.1. The right one shows on version 20, and you can see the immense speed up ratio. Okay, moving on to the mesher. So now we have the capability of running the mesh on the scheduler. So what does this mean is that, so before, if you know that you usually can calculate your cases just by sending them to the scheduler to be able to have the designer freed up. Now you also have the capability of using this with the mesher. This only works for 3D models, but it also makes sense more for 3D models since usually 3D models are more tricky and take a bit more time to mesh. And what does this offer is that you can run your mesh, you can send it to the scheduler, you can continue working on Designer. Afterwards, you just, similar as checking results, you're checking the mesh. You check, then you can modify again and see if you can need to make any changes to the mesh, and then send it again back to the scheduler. All of this within, and the Designer is still freed up for you. You will require an extra license in case you need to run this on a cluster machine or on a remote machine, sorry. Doesn't have to be a cluster. Okay. Then moving on to the APV. So first of all, we have analysis templates and equations. These can be easily implemented just by dragging and dropping back into the project tab here. Just from the toolbox, you can just directly implement them, and it offers just a quick way of implementing your equations and your analysis templates. At the same time, I'm going to show here a case where I have this motor here and we're studying the joule loss versus the vibration, and what I'm varying, the varying factor here is the case thickness. So let me go to Designer. In this case, just give me a second. So now I'm here in Designer. As you can see, I have here my 3D. So what I'm doing is first I'm calculating the electromagnetic forces on a 2D model, then calculating the joule losses using this 3D model here, and I'm doing a structural analysis on this 3D and the model in the end, as I said, to compare both joule losses with the vibration or the acceleration, basically. So if I go here, go to my study, we have the APV, or through this shortcut here, this is one of the new features. So if I maximize here, you can see through this APV, you have all the case parameters. So here, for example, you have your conditions saved. And no, let me make this a bit wider to make it more. Move this, this, and this, this. So here I have all my conditions. And what I can do with these conditions is basically I can modify them in case I forget a certain property. Let's say, for example, I forget the rotation speed, displacement type. All of this is saved here, and you can just with this checkbox just modify it. Also, at the same time, we have a shortcut here implemented for circuit, just to check the circuit here. And also at the same time, another shortcut implemented for the model itself. So just if you want to have a view of the model. And what we're offering here is basically a capability of doing all the work within this APV space. So if I view my results, this takes a bit of a second. As you can see here, I have my results saved. Currently, I'm displaying case 1. I can, for example, add a result item here or add a response graph. Let's say I want to compare case index with joule loss, for example. I press OK. I get a graph here showing the different joule losses with each case. So as I said, this is all implemented within Designer, and you have it all within one single window now. So you can continue all of your work inside of it. Say we move this step here for a few steps. You update your contour plots as well. Now it's freezing a bit, but this is a bit of a heavy model as well. Okay. Let's move on to the next point. Let me go back to the presentation quickly. So back to the next topic is going to be efficiency maps. So as you know, we have two types of efficiency maps here: speed priority mode and accuracy priority mode. Speed priority mode is, of course, for concept and system design. Accuracy mode is more for motor design. Speed priority offers a rough estimation. So basically, you would do a sort of a parametric geometry. You would change the geometry parametrically and see what types of you can get several efficiency maps quickly. So to just judge this motor and see, okay, if this is something that I would like to use in the future. But if you want to calculate the losses accurately, you want to consider inverter harmonics. You can now do this in accuracy mode. You can also create a driving mode simulation and calculate the efficiency at each driving mode point. So as I said here, so in speed priority mode, you're getting a response table of motor characteristics. So it's just a very fast simulation. So you're not considering any transient effects, such as eddy currents, for example. Here in accuracy mode, you're going into much more complex simulations. And what you're doing here is you're accurately calculating, you're doing a transient calculation at each operating point and calculating the losses at those points. So again, let's move back to Designer. So here I have a speed priority map set up. What we have here is, let me just load the results quickly. So I have my results set up. One of the new features is that you can consider also AC copper losses within speed priority mode. PWM was available since JMAG 19, I think, if I remember correctly. So here you're adding approximately calculating PWM losses for the eddy currents by just inputting a DC bus voltage and specifying a carrier frequency. Also, you can approximate AC copper losses by this analytical method here, where you just input the shape of the coil, you supply the conductivity. You can specify also around the conductor if you'd like. And with all of these parameters, you're estimating also the AC copper losses. So let me just show quickly the efficiency map containing all variables. And if you see here, you can specify, for example, PWM eddy current losses. Hysteresis losses are not affected with this a new method, but since you'd have to do a new calculation for it. Let's see here, for example, this is one of the, this is the PWM losses. Okay, and then let's compare. Let me open this a bit wider. Yeah, here. So here what I'm doing is I'm actually doing, I'm comparing an accuracy mode map with a speed priority map, just to show what sort of differences are we expecting. But as you see at low torque, high speeds, or low speed, low torques even, and even high torques, you have a discrepancy of up to 2%. So if you are looking to be in the 1% range, the very accurate range, you will need to move on to speed accuracy priority mode. But this gives you, let's say, a very good initial estimation of your motor behavior. Then let's go to accuracy mode. A second for it to load the graph exactly here. So here's the graph. Now you have the capability of seeing the contour lines, what percentage is at each line here. You can also show analysis points for each point. Let's jump to one of these cases here. Go to case. So now I jump to case 108. I can see how my circuit current flows. And as you can see here, let's zoom on to this point here. I'm actually doing a control circuit simulation within this efficiency map calculation. So let me show the circuit here. So what we have here is a basic controller, where I have my inverter, and here what I'm using is a JMAG-RT block to calculate the initial transient period of the simulation. So with all voltage drives, you have a bit of a transient effect in the beginning. And what I'm doing here is, first, for the initial transient period, I'm calculating using JMAG-RT. And once I reach a certain tolerance, or I reach a bit of steady state, I have my motor here, from which I can calculate. I can move on to my FEA simulation with. So for the initial, that's why in this graph you saw a bit of like a straight line. I'm going to show it again. The straight line in the beginning, and then it moves on to the normal curve that we're expecting. So again, let me show it again here. Let's say, for example, for torque. So as I mentioned here, for this initial part, JMAG-RT is being used. Of course, the idea of using JMAG-RT is that you're skipping the transient period, so you're saving a lot of time. And then once I reach steady state, I can do my FEA calculation. Okay, and then the last part of efficiency maps is that now we have the capability of, let me show this efficiency map here. We have the capability of calculating the drive cycle of each, the efficiency of the drive cycle points. So for example, let me get the Excel file here quickly to show it. One moment, please. So here I have my drive cycle, so speed against acceleration, speed against time, sorry. That is speed, that is the speed and that is the time bar. And what I'm doing here is that I'm inputting this inside of JMAG, and what JMAG is doing then afterwards is calculating the efficiency at each, is taking the efficiency map that is already calculating and displaying these points then afterwards on the efficiency map. So here, point display with marker. I have my points here calculated and I can see my efficiencies at each operating point of the drive cycle. Okay. Going back to the presentation. So we have winding and coil modeling now. So with the winding editor, we have, before you were limited to these block coil shapes. Now we offer the capability of parameterizing the winding editor also with the wire template, which is our 2D method of calculating sort of coil shapes. And with this, you can create a parametric calculation, varying the slots and poles, and while also changing a bit of the rotor shape. We also, for the winding editor now, there's a support of 6 and 9 phase motors. So basically, what I mean is that this shape, this shape, this shape, all of them could be created within one single study. Then to the coil end template, we have improved the meshing capabilities of coils. So now you have a more robust mesher that can that handles better complex coil end shapes. You can create high slot fill factors. You can create low end height windings. Also, you have a custom winding table editor for arbitrary winding configurations. Let me show this in JMAG. One moment, I just need to find the file. So basically here, I have parameterized my winding just by parameterizing the slots and the poles, and just by varying these, JMAG adapts automatically to this according to my coil pitch that I've specified in the winding editor. Then moving on here to the 3D end windings. So here I have a complex shape. If I go to the geometry editor here, first of all, if I go to the coil and I edit this, so first of all, the geometry editor is much more robust in creating these types of geometries. At the same time, for our winding configuration here, we offer a table through which you can input. Let me make this a bit wider here, a bit more wider on the side here. And here you're just inputting the in and out of each coil. This can be done with a CSV import, or you can just manually do it. At the same time, you get a preview of how this is going to look like in the end, which makes it, let's say, just makes it a much more easier to create your complex winding shapes. Okay. Then moving on to the next topic, material modeling. So when modeling is irreversible demagnetization within JMAG, so within the previous versions, JMAG offered sort of a simple method to model nonlinear magnets, which was calculating certain parameters, which is, for example, the relative recoil permeability, drooping permeability, the coercive force, and the residual permeability, and also the round radius. You specify these 5 factors here. Once, and JMAG automatically generates a curve from it. Sometimes it was a bit tricky to calculate these variables. So, and also because we want to be, let's say, more accurate, we now offer the possibility of just importing a direct BH curve from a CSV file. So this is called the point array. So each point is calculated and each point is inputted. This, the previous method is called the bilinear approximation. And as you can see in the graph here, for you can get quite a bit of some discrepancies from the bilinear approximation to the point array, just because you're assuming a graph and you're doing a bit of curve fitting. So in my example here, we did a bit of a small test. We're trying to demagnetize a surface magnet motor. And what I'm doing here is just for a certain period of time, I'm operating at 60 degrees, then I ramp it up to 140 degrees, and then I jump back down to 60 degrees again. And what I'm seeing is the effect on torque and the demagnetization ratio. So if I go quickly to JMAG, so here's my study. I can show you quickly the materials here. So you still have the bilinear approximation available, and you also have the point array option. So if I edit this, as you can see here, I just implement just the points, and JMAG just generates the curve from it. Before, you would have had to calculate these 5 variables here, and from it the graph was generated. So let me generate a second window. Here, let me go to case 2, then contour plot here, contour plot here. Let's jump to 0.200, for example. after the temperature. Oops. This is case 1. So if I see my demagnetization ratio, I have a maximum value of almost 9%. Here I have a maximum demagnetization of 6%. So for very accurate magnet modeling, we of course recommend the point array. I can show quickly the effect on torque. So this is the point array model, and this is the bilinear approximation. This is to be expected because, yeah, the point array was demagnetized a bit more. Okay. Then to the topic of optimization. So we now created a new predictive model which reduces geometry collapse. So one of the main issues when doing your optimization was the combination of several CAD parameters which generate broken geometries or geometries that are not even feasible. And there was no way of knowing before. There was no method. You just have to sort of guess between your range, and sometimes even within, if you're within your range, a combination of two CAD parameters that intersect could create a broken geometry. And what we do now here, what we offer here now is the capability of first finding the range by means of a script, which uses a genetic algorithm to find the range of your CAD parameter. You would then create a predictive model, and this predictive model then generates several cases and does a result, sort of a 0 and 1, in which you have 0 is a broken geometry, 1 is okay geometry. And from this predictive model, JMAG can afterwards generate cases which are all okay, where there are no issues with them. This, of course, then saves you a large amount of time because, first of all, you're basically skipping the step of generating a generation where you have several broken geometries and you have to cancel them out, and then you would have to continue searching until reaching your optimal design point. What this is doing is just skipping out this initial trial period. So let me quickly go through this within JMAG. So if I check scripts here, there's a tutorial that explains this. So first of all, you can search the size range by GA, by a genetic algorithm. You're searching for the maximum minimum value of a certain CAD parameter. And then you're creating a predictive model here. This predictive model generates this type of Excel file, where, as I said, you have your CAD parameter here, and then you have the result. If it's 0, that means that this geometry is broken. If it's 1, that means that this geometry is okay. What JMAG then uses afterwards is it uses this predictive model afterwards to generate cases to ensure that all the cases are valid. Okay. Then the next topic of topology optimization. So you have a much more varied design space. Your design space is basically unlimited because in the topology optimization, you are switching between, you are just changing the flux barrier, you're switching between material and air, so you have a very wide design space. You're not limited to CAD parameters. JMAG offers two methods to do topology optimization. The first one is the NGNet method. The second one is the sensitivity analysis. So the NGNet method uses a genetic algorithm. It's a global optimization method. The gradient descent, the density method or sensitivity analysis is more of a gradient method. It uses gradient descent to find the local maxima and minima. You have the NGNet is a multi-objective optimization calculated with it. Density method is a single objective optimization. Calculation cases, of course, because the NGNet method is much more varied and it's much more robust, then you're actually calculating a much wider range of values, so you have a lot of cases. Density method is a quick and initial way of going into topology optimization, through which is done actually through a PC, like the NGNet, and not like the NGNet method, which is done through an HPC. So what we usually recommend is that you start with the density method to sort of, let's say, get your foot into topology optimization to see what your initial results are. And then once you reach a certain result, you can then move on to the NGNet method and you can then move on to the NGNet method and do your more complex calculations. Of course, both are support magnetic and structural analysis, so not just magnetic. And here we have an example of a result. So as I said, the NGNet explores a wide range of design areas using the genetic algorithm. And usually you input an objective function such as maximum torque or maximum and minimum torque ripple, and you get a varied solution of iron and air. The same is for the density method, but as I said, it's a gradient method, so it converges much faster and can be done on a much quicker scale. So here I just have the result of the density method, which starts with this formation, and then it goes on and on until it finds this final result. I see here how the values change within time or within each calculation. Okay. Thank you very much for listening. We will now take your questions and try to answer them through the chat.
Okay, thank you, Ahmed. So yes, we had several questions. I tried to reply in the chat. Maybe there is one more here. So does JMAG new version contain any feature or improvement regarding modeling induction heating process? Okay, I will check that in details. I'm not sure this year there are some improvement concerning induction heating, but the year before we had many improvements like dual frequency heating. Yes, we had several improvement, but not so much this year, I think. I will check in detail. And
I think it's more last year.
Yes. Do you remember the ones, Ahmed, or?
I can't name them exactly, but this year I would say it's more the improvements last year. There are some, yeah, I can't, we have to check.
Yeah. We'll check and get back to you for sure. Okay, another question is about maybe fluid dynamics, CFD calculation. No, there is no CFD solver in JMAG. JMAG is not for CFD or fluid dynamics. And however, JMAG can do some structural calculation, thermal calculation as well. But the thermal calculation is only handling conduction and radiation, no convection. So no convection because no fluid dynamics, no fluid. However, the developer are still considering this this possibility, and they are thinking about yes, maybe one day perhaps embedded CFD solver in JMAG. Okay, so next questions. Is there any template modeling for axial field machine and optimization in JMAG? So the question is there any templates? So is it for shape or template analysis? Anyway, regarding templates, at the moment, not yet for axial gap motor. But I think this is coming. Maybe the template will switch to 3D quite soon. This is maybe this year or the year after. But 3D template will come, and maybe with axial gap motor, but not yet. Okay, another one is just wondering if there is work going on making only single slot conductor rather than making conductors in all slots, especially for AC losses, as if it often very time consuming. Yes, one slot calculation is possible, and we've got some customers that making that for sure. That's possible. So yes, one slot is possible with all the strands inside the slot. Okay. There is a question saying that he missed the beginning of the answer. I would appreciate if you could send me a quick email. Okay, maybe I will find the corresponding question if I check the history, or maybe you can ask it again. Put it in the
It's
in
in
the
the
chat.
induction heating.
It's induction heating. Yeah, maybe okay. Yeah, so for organic induction heating, not so much this year. Last year, maybe we can send you the presentation of the new feature of V19 and the one before, so we could show you what was new previously regarding induction heating, but not so much this year. Okay, and yeah, I tried to reply also to all previous questions. Feel free to add some more if needed, or to add some comment if my replies are not enough.
Can we couple, I think there's a question here, can we couple JMAG with other solver like ANSYS for multi-physics problem? Yes. Not ANSYS. You can export your JMAG solution to ANSYS. A direct coupling, I think, is not possible.
No direct coupling. Of course, ANSYS is a competitor regarding finite element, regarding magnetic calculation. So the developers are not going to work together. However, there are some coupling solutions using third-party software or using temporary file, exporting Nastran data, CFD file. The third-party software is the MPCCI interface. This is an interface completely dedicated to mappings between different softwares. And JMAG has the multi-purpose file export tool that allows you to map any quantities you have calculated in JMAG onto a third-party mesh. This multi-purpose file export tool can also import some quantities. For example, heat transfer coefficient density could be imported in case you are importing data from fluid dynamics computation. So you can also import that kind of data inside JMAG and then run your thermal calculation. Okay, so do we have covered all the question? I think so. Do you see any more question, Hamid?
I'm looking now, but I think we have everything. Maybe we need to wait another minute in case somebody else has another question. Oh, wait. How to extend material data? Oh, okay, wait, we have one here. How to extend material databases access? Is it possible to purchase some pH curves and loss tables for very high frequencies for some electric steels, frequencies and range?
Yes,
So I think if you're meaning by the material database within the JMAG, I think it's confidential, but if you want to purchase it, I think you will have to directly talk with JSOL if that is possible.
yes.
But usually you can get this data.
If you have any material you are interested in, feel free to come back to us with the name of the manufacturer, the grade number, and as many details as possible, and we will communicate that to JSOL, and JSOL will try to contact the manufacturer in order to embed those material into the JMAG material database. Yeah, so that's possible. If of course, if you have already the data, you can make your own database. You can create new materials, and you can also use shared material database. If, for example, you've got a shared folder on the network, JMAG is able to connect to this shared network, and you can access to those materials, but still you need to have the data. If you don't have the data, but just the name of the material, of the manufacturer, and the grade number, maybe we can communicate with JSOL, and JSOL can try to contact the manufacturer to get the data and to have it into JMAG. Still JSOL is interested to develop the material database, so that's a benefit for JMAG, of course. So really feel free to do that. Maybe JSOL will then include this material in the database.
Then we have a question, how many modules can we couple in JMAG, like structural, plus thermal, plus electromagnetic? So you mean at the same time? Direct coupling can be done within 2 modules at the same time. If you're exporting, then you have the flexibility of doing several types of all the types of studies.
Yes, I think that's
no
possible.
limitation.
I think that's possible. The structural plus thermal plus electromagnetic. There is a new type of analysis in JMAG, which is thermal. Okay, let me check in JMAG quickly. So, okay, I will find the exact name of the study, but there is a study which is making structural and thermal at the same time, and that's to be coupled with the electromagnetic. So basically, yes, you can do that. So feel free to ask any other questions.
Does topology optimization deal also with magnet materials beside iron and air? I think yes. Let me double check this point.
Yes, I think so.
I think up from JMAG-20, it's possible to include magnet material. This was a limitation before. I think this is possible now in JMAG-20.
So regarding the previous question, the analysis name is thermal stress. So you can make a thermal stress, so including structural and thermal, and that's to be coupled with the electromagnetic.
Then there's a question, are there new circuit components in JMAG V20? No, none announced.
Okay, however, you can create your own macro component, of course, in the circuit editor.
Then, considering control co-simulations of electrical machines, what are recommended options? 1, co-simulation with MATLAB, or trying to implement digital controller into the circuit editor. Those are very different types of simulations.
Yeah,
so
many possibilities.
Yeah.
Sorry.
The second one is more FEA. Yeah. So the first one is actually you're using with MATLAB. It's going to be JMAG-RT. You're going to import your JMAG-RT into the simulating circuit and do your controller from there. That is, let's say, the normal way of doing things. The second one is if you're implementing your controller into the circuit editor, then you're doing an FEA PWM simulation. So you have to consider that this will take a significant amount of time, but you're getting very accurate results. So if you're evaluating losses and motor behavior, then sorry, not motor behavior, but if you're evaluating losses, then we would recommend the second option. But if you're just evaluating your control circuit, then you can do with MATLAB. And if you can, of course, add if you have anything extra to say about that.
No, nothing to add. Yeah, many possibilities. Using RT, the behavior table, using direct co-simulation, using only JMAG, because JMAG has the possibility to make the control directly inside the circuit editor. Yeah, that's depending what you really want. You can also make point sequence, put point sequence in your drive. So that's not full control, but then you can take into account the effect of the control of the PWM, for example, in your magnetic calculation. So yeah, many possibilities. Maybe you can contact us and we can have a discussion, because that's really depending on what you would like to do. So maybe for your communication, I will put the email of the support. I will put that in the chat.
There's a question if it's mandatory to use control circuit for accuracy priority mode. For efficiency calculation, no. It's a suggestion we make, but you can use a normal sine wave drive. This is just showing the capabilities of accuracy mode, that you can go into much complex loss analysis.
So regarding, we have a question also regarding the new feature regarding RT. Yes, there are some new feature regarding RT. That's concerning the lookup table. So the circuit, the component to be placed into the circuit editor, into the circuit software. So the speeding up of the circuit simulation has been improved. It means that, of course, using ERT table is for making the calculation with the circuit quicker than a direct link. So the calculation was not so quick as using ideal motor component, but it was not so bad. Okay, it was not like full coupling with FEA calculation. However, it was not exactly as quick as using ideal park model components. So now this time it has been improved, and it's really comparable to those ideal components. So using this circuit component has been improved. And also one more improvement regarding RT. This is dealing with maybe a sensor like resolver. So many coils are embedded in those sensor. By removing or ignoring some of those coils that are non-excitation coils, you can reduce the calculation time for the generation of the RT table. And that's one of the feature as well for RT.
Does the circuit editor support some control structures, state space methods on macros, with example adaptive control and conservative size? If you can code it. So we have you can generate macros where you can just specify Python code and it will do whatever you, let's say, need. So if you can code it within the JMAG editor, it will definitely work.
So there is maybe there is another one. Is it mandatory to use control circuit for accuracy priority? No, that's not mandatory. You can use a direct three-phase current in the accuracy priority. Accuracy priority is kind of parametric, and of course you've got some additional feature for generating automatically your efficiency map, but this is a kind of parametric. So accuracy priority mode, in fact, there is no assumption. You can do nearly whatever you want. It's just a kind of parametric calculation with some feature for outputting the maps. Okay, do we cover all the questions? Can you see?
I think
Ahmed,
we did.
it's okay?
I think it's okay, yeah.
Okay, good.
Okay.
Feel free to come back to us anyway for any questions. So just let me share. I just would like to share you the web page. So maybe I need to be participant, presenter. Okay, I will. Okay, can you see my screen?
Yeah, it's there.
Yeah, it's okay.
Yeah.
Okay, so here is the JMAG web page. So if you go to download support, download, of course you can download the latest version. So if you are if you would like to use to download the latest version, the link is there. Please note that you need to update your license server, license manager. The LMX version v20.24 is required for the JMAG v20. Please update your LMX version. And then if you would like to go to the introduction of v20 again, here you've got a page with a summary of all the features. You can find also here full presentation with all the topic detailed. And then here you can access the tutorial if you would like to try using those new features. So there are some tutorial completely dedicated to those new features. Okay, so thank you for joining this session, and feel free to come back to us if needed.